Hello, good afternoon. Fine, more or less. You? Okay, so I'm actually sharing my screen. You should be able to see essentially yourself, right? Okay, okay, perfect. We are still missing a couple of people. Today I had, let's say, a personal problem. I had to connect from somewhere else, and the problem is that the connectivity is not very good. So I will switch off my camera, and also I guess it's better if you switch all of your cameras off. So maybe we save some bandwidth. Let's hope that this works. Let's hope that, because technology is not always my friend. But at least today I was able to share my screen without like spending 10 minutes, which is something good. Okay, we are just missing one more person. Okay, now it seems that we are all here. So, as I was telling just 1 minute ago, for some personal problems, I had to connect from a different place, and my internet connectivity is not that good. So I will switch off my camera, and also would prefer if you switch off yours, just to try to save all the bandwidth that we can, and so you can hear me more or less decently. I mean, if you have problems, if at some point you see my voice, you don't hear my voice, better to say, just tell me, and I don't know, I will connect with the phone or whatever. Uh, so first of all, well, good afternoon to all of you, and do you have any question, any doubt about what we saw last day about networks? Still no nightmares with networks? I, I, no, that's a shame. Then I'm not yet. Okay, well, let's see if today is my last chance. Yeah, please go ahead. Yeah, sure. Actually, that's a good point, because there were a couple of things that I didn't explain the other day, so I just wanted to start again with this presentation. So the betweenness centrality, the idea is a node is central when there are a lot of paths that go through it. So in a sense, it's like, imagine that you are a node in the network, and that if two other nodes want to communicate between them, they have to go through you. that will be the perfect case, like of a perfect betweenness centrality. Imagine a star in which you have a central node and then all the other nodes connected to that central node. If two nodes want to communicate between them, what they have to do is to go through that central node. There is no other possibility. So that node in the center will like control, if you want, or has the possibility to control all the communications in the network. So imagine like this meeting that we are having via Teams. At the beginning, when we started the meeting, I guess that my computer had to send a message to the team server or whatever is wherever is located. I guess it's here in Madrid, and uh, and then you also had to connect to that server, and then we probably exchange IPs, and then we start communicating between each other. But the point is that at the beginning, the only path that you have between nodes goes go through that central node. So it's like, okay, I know that according to this framework or this way of seeing centrality, a node is central if it can somehow control a lot of shortest path, or if a lot of shortest path have to go through that node. Because then, of course, you are like the king. You control all the communication and you can break down the network if you want, or you can just filter messages, or you can do whatever you want. But in any case, you are central because you are controlling the movement of information. So how do you calculate it? It's actually quite, let's say, computationally heavy. You have to calculate all the shortest path between all pairs of nodes. And then you just count how many of them pass through the node for which you want to calculate the centrality. So like in the network that I have here in the screen, let's suppose that I want to calculate the centrality of this node that is here in the middle. Well, I started by calculating the shortest path between this node and this node. And actually, okay, I have to go through this. So I like tick one, I mark +1. Then between this node and this node, also I have to go through that. Okay, that's a 2, 3, 4, and so forth. You count the number of shortest paths that go through it. And then you normalize according to some metric. And then you say, okay, the node through which most shortest path have to go will be my most central node. That in this case will probably be this node here in the middle. So it's actually quite simple. The problem is that if you have a very large network, is the problem that we always have. If you have 1 million nodes, you have to calculate 1 million times 1 million shortest path and count how many shortest paths go through the node for which you want to calculate the centrality. So it's of course computationally quite expensive. But in some applications, especially in terms of communication, imagine a communication network, this is super important. Or even any kind of transportation network is like, okay, if you want to go from Europe to the US, there are just a couple of airports through which you can go, because especially now there are not a lot of flights. So if you want to go to the US, you have to go either through London Heathrow or France, like Paris Charles de Gaulle. I don't know if Madrid has a flight right now. So it's like, okay, these three airports will be way more important just because if you want to cross the Atlantic, you have to go through them. That's the basic idea. Clearer now? Okay, perfect. You're welcome. So as you can see, actually, many metrics or ideas that we calculate on networks, they're not actually that complicated. So they're like intuitive ideas that we might have about what you can calculate on a network. That is, okay, if I have a network, I will do this. And then there is like the mathematical part that at some point it can be a little bit more complicated. But most of the time is just what you would do just by looking at the network and say, okay, this node seems like in the middle because it's connecting things. That's exactly what we calculate. So it's not, I mean, it's not like very sophisticated mathematics. It's more like putting into numbers what you would see by naked eye somehow. So, okay, we have seen some centralities, and there are a couple of concepts, actually just two of them that I want to review, just because I think that you will use them in the next classes. So just to be sure that you have a more or less clear idea, especially of what modularity is, and so you are not surprised. So modularity is very simple. The idea is that we want to detect communities in a network. And by communities, think on let's skip the definition 1 second. Think on social network. What will be communities? Well, probably communities will be group of friends, right? So you have a lot of people, but some of them are strongly connected between them, because you know that if you have a group of friends, all of them are friends with all other members of this group. And then maybe there is one person that has a friendship with another person in another group. But essentially, these are like quite isolated groups of people that are very well connected between them, but let's say loosely connected between communities. So this is the idea of communities. So communities is a concept that is actually not too well defined. There are a lot of discussion about this, but the idea is that you have a group of nodes that are highly connected between them, but loosely connected with other nodes that do not belong to the same community. So to have an idea, here on the left in this network, you have that nodes 1, 2, and 3 form kind of a community. Here on the bottom, 4, 5, 6, and 7, you have another community. And why I say that they are communities? Well, because like for instance, in the top part, all nodes are friends or are connected with the other nodes of the community. Here on the bottom, okay, 7 is slightly more isolated, but you can see that more or less 4, 5, and 6, they're well connected between them. 7 is there around. But from the top community and the bottom community to the bottom community, there is just one link. So as you can see, these 3 nodes on the top are very well connected between them, but they are not that well connected uh, with the bottom part, with the remainder of the network. So you can easily see this in social networks, for instance, but there are many other examples. For instance, if you see at protein-protein interactions, and you construct a network in which nodes are proteins, and you connect pairs of them when they interact somehow, then you have to define what is interacting, but is like, okay, participating in the same function or things like that. You have quite strong communities. And why is that? Well, because for instance, all the proteins that are related to energy production in the cell, they will be strongly connected between them because they have to interact in order to control the energy production. But another function that is, I don't know, maybe the reproduction of the cell or any other thing that you may have, well, maybe you have some connections because, of course, reproduction depends on the availability of energy, and therefore you have to get some signal. But they are like a different communities. They are a group of proteins that are working together, but they are different. And so there is this like loose connection between groups of proteins, but between each group, they are very well connected. They are strongly connected. They share a lot of information. So as you can see, this definition is not exactly precise, if you want, in a mathematical way. It's more like a concept that you may have just looking at networks. So there are some problems, but in any case, there is a metric that is more or less well accepted that is called modularity. And the idea, well, without entering into the details of the mathematical formulation, it's just a metric that tells you that how strong are the community structures inside the network, such that if you get 0, you don't have any structure, it's like a random network. And if you get 1, it means that you have communities very well defined. And the best way of having communities very well defined is, for instance, when you have 2 groups that are disconnected. So imagine that here in the middle, I cut this link between 1 and 4. Then I will have a group of nodes very well connected between them and with no connection with the remainder of the network. And the bottom group will be exactly the same, very well connected, but not no connection with the remainder of the network. So this will be like the perfect case of modularity, like one group on one side and one group on the other. Of course, usually you don't get that. It's quite weird because if you have such a perfect division in communities, maybe your data have something wrong or there is something like fishy, because in real world you never get such a perfect division. But this is the idea. And by the way, if you now I have to thank you for asking me about the betweenness centrality metric, because if you think about that, nodes that have a high betweenness centrality are actually those nodes that connect different communities between them. So probably here 4 and 1 will have the highest betweenness centrality. Why? Because if I want to move from one community, the bottom one, for instance, to the upper one, well, I have no other solution than to go through 4 and 1. So like these two nodes are controlling, they are not just part of a community, but they are also controlling communication with the other community. And therefore they are important. Because if node 1, for instance, or node 4 fail, then you disconnect the network, and then you may have problems. You're not able to send information from one side to the other. So just for you to know, there are many algorithms to calculate modularity. There is still no like perfect algorithm, not at all. So there are many solutions that have been proposed. Some of them are more efficient. Some of them are very good at detecting communities, but their computational cost is huge. Actually, one of the, I would say, of the best one, but whose computational cost is huge, is actually using the betweenness centrality. So the idea is that I take this network, I calculate the node with the highest betweenness centrality, let's suppose that is 4, and then what I do is that I destroy this node. And then I will have 3 groups, one here on the top, node 7 that will stay alone, and nodes 5 and 6 that will also form like a mini community. So as you can see, just by deleting the node with the highest betweenness centrality, you can kind of detect communities. It's not that simple usually, but this is the idea. So you try to break down the structure of the network by attacking the nodes that are essential for the communication inside the network. So this is modularity, and then there is another uh, similar somehow concept that is called motifs, and motifs have been found to be super important in biological networks, although uh, let's say it's complicated. So let me explain. Motifs per se are very simple. They are just, the definition is that they are pattern of interconnections occurring either directed or undirected at a number significantly higher than a randomized version of the graph. So the idea is, I take this network and then I start calculating, for instance, triangles like this number 5. And I count how many of them I have. Or I can start with this number 1, in which I have like one node that is connected to 2 other nodes. And I start calculating how many I have in the network. Now, at times, you find that some of these patterns appear in the network in a number that is far higher than what you would expect just at random. So remember, this should remember you a little bit about the z-score that we calculated the other day. So it's like, okay, I compare, let's suppose that I find 10 instances of this motif, and then I go to random networks with the same number of nodes and links, and I find on average 2. And then it's like, wow, in my system, I have this pattern that is appearing with a frequency that is quite high. Then maybe there is something going on with this pattern. So maybe this is important somehow in the network, because otherwise we won't find that pattern so many times. And actually, this was a series. Well, it started all with, of course, one publication, but then several came out in which they analyzed biological networks, different types like gene regulation, protein-protein interaction networks, things like that. And they found that there are some patterns that are really frequent in this kind of real network, much more than what you would expect at random. And actually, you can see that a pattern of this kind is a regulation. That is, you have one node that is regulating or is somehow influencing or is causing or whatever you want to call the dynamics of to others. So it makes quite sense, like in a biological network, that you have one protein, for instance, that is modifying the activity of many other proteins, and then you will have this kind of structure. Uh, there were other structures that they found things like this, and they demonstrated that each one of, well, not exactly each one of these patterns, but many of these patterns are associated with a specific function. So it can be regulating, like downstream, you regulate the different proteins. If I'm not wrong, number 5, but don't quote me on that because I'm not sure, but I think it was number 5. Uh, it was very good for reducing noise in the activation. So essentially the idea is that I have a signal and I spread it in 2 nodes, and then I use the second node to also regulate the first one. And in this way, I can make sure that if I have a signal that is like a transient, a very fast, like noisy peak or whatever, this peak will not propagate to the end because of the dynamics of the elements that we are analyzing. So essentially, the idea is that each one of these patterns, if you find them in a quantity that is not what you would expect in random network, then you may start thinking that this pattern is important for something. Uh, of course, then the problem is that you have to go back to the data and try to understand what is the function or why that pattern is there. But at least this is a very good way of like spotting patterns that are not normal in the sense that they shouldn't be there, but they are there. And so probably there is a reason for that. They are doing something that may be interesting. And so motives are quite powerful, but the problem is that you have to go, let's say, you have to interpret what they mean in the system that you are analyzing. Like with communities, is way easier because a community is something that you can see. Okay, it's a group of nodes that are strongly connected together. That's not much to be interpreted. Motifs are a little bit more complicated. Yeah, and the last slide were a couple of 5 references for you, in papers that if you want, you can find them in the internet for free, I guess, all of them. And they are quite good if you want to explore more complex networks. Like this paper is quite good because you have the definition of hundreds, I would say, of metrics. They are called here measurements. Here you have a complete review, although it's a little bit old, but it's still quite good about all the aspects of networks. You have the seminal paper of Albert and Barabas in which they described the scale-free networks. So, I mean, if you want to dig a little bit into the topic, you can start from this. But okay, now the topic of today is a little bit different. So first of all, do you have any question about what we have seen up to now? So the important point is that you have to be confident. Let's say it should be clear to you that once you have a network, you can calculate metrics on the networks. You can normalize the metrics that you have obtained in order to avoid problems with the number of links and so forth. And then, of course, you have the funny part that is try to understand why a network is like that. And then you have to go back to your system and say, okay, my network was a set of genes, so let's try to understand what these genes are doing or whatever. So if you have no more questions, I will then move to another topic that I think is much more powerful in the sense that will allow you to really analyze network in a way that is not the one that we have seen in the last 2 sessions, because it opens up a lot of possibilities. It's much more flexible. I actually don't have presentation for this because I think it would be very easy for you to visualize. I just have to tell you, and it will be more or less intuitive. So what we have done up to now, especially in the exercise or in the data that I've sent to you, is a kind of cheating, if you want, because I've sent you a network or 2 networks or whatever. Uh, but I already sent you the network. So I'm supposing that I can extract a network representation from a system without any problem. And this is Uh, Possible in many situations, but it's not always possible, and in many cases, it's not always useful. So let's suppose that we are analyzing a system that is somehow explicit, like for instance, air transport. Well, it's quite intuitive to say I will decide that nodes of the network are airports, and then I connect pairs of nodes, that is pairs of airport, when there is a direct flight connecting them. And what do you have to do in order to extract this information? You just go in the internet or whatever. You can even go to the airport, check if there are flights. I don't know. You go to Madrid or you enter the website of the Madrid airport and you check if there are flights connecting Madrid to Paris or Charles de Gaulle. Yes, there are. Okay, here I have a link. Are there flights between Madrid and I don't know any other city? Berlin, for instance? Yeah, there is. Okay, add one link. So the point is that links here are explicit. They are there. You just have to look at the data that you have, and you just take the links and you put them inside your object, your network X object, and that's all. So super easy. It's just that. The point is that for some systems, we don't have this explicit information, or we don't want to use that information. Let's take another example. Let's suppose that we are analyzing a transportation network of a city, like the underground network. Then you can do the same thing. You can say, okay, each node is a station, an underground station, and I connect pairs of them when there is a underground line that connects both of them. Uh, okay, this will give me the backbone, if you want, of the network. Actually, is exactly the same as taking the map from the internet and just mapping this into a network. Actually, it's already a network, so you don't have to do a lot, and that's okay. You have your network. But then what I want to do, or usually what I want to do when I study this kind of systems, is to know which stations are most important, but not just most important because they connect a couple of lines or things like that. No, they're important because in the morning, in the peak hour at 9 o'clock, there are a lot of people that go through that station, even though maybe it's not extremely well connected, but is a station that is relevant because in the city you have I don't know, the financial center of the city or whatever. So you will have a lot of people going to that station. You cannot infer that just by looking at the map, because in the map all the nodes are the same and they have a name, but that's all. So what you have to do is to go back and see the dynamics of the system, and from the dynamics extract the information that you want, and then use this information to create a network representation. Let's go with another example that is more related to what we will do today. Let's consider the human brain. For the sake of simplicity, let's suppose that we divide the brain in different regions. So you may have, I don't know, like in the data that we have, 64 regions that map more or less the cortex of the brain. Then the initial representation will be, okay, let's try to see if two regions are connected. How can I do that? There are techniques. Essentially, what I can do is to check if there are fibers connecting one region to another. And then I will say, yes, this part of the brain that corresponds to the visual cortex, so it reacts when you see something, it's in charge, let's say, of recognizing objects or whatever, is connected because there are fibers there to something related to memory, for instance. And then you say, okay, that's good. I can reconstruct this network of connections, and this will give me the backbone of the connections between the different parts of the brain. And actually, this is called the connectome. But the real problem that I would like to see is, or I would like to study is, do I really always use that connection? Because maybe I use that connection. I mean, the connection is there, but maybe it's activated only when I see something and I have to remember that I've seen that face in the past. Otherwise, maybe that connection between the visual part and the memory will not be activated. If I'm listening to music with my eyes closed, probably the visual part will not be much active, and therefore the connection between the visual part and the memory will not be active. Then I don't want to see like the static network of possible connectivities. No, I want to see which connections are active in a specific task or in a specific condition, or just if I'm in a resting state, that is, I'm doing nothing, see whether this connection activates at time or not, or whatever. I mean, everything that you may want to study. Differences between control subject and patients suffering from some disease or whatever. So, do you see the difference? One thing is to see or to describe the backbone of possible connections, and another one is to describe when actually these connections are used. Because actually, if you go back to the brain and you see the backbone of all possible connections, essentially is an all to all. So, it's not, I mean, I'm simplifying here, but almost any region of the brain is connected with any other region because at some point in your life you will need that connection, but this doesn't mean that all connections are always active. They will just be active when they are relevant for the task that you want to do. Are you following me up to now? Okay, if you have doubts or is not clear, please interrupt me because so I mean it's an important concept and we are going a little bit abstract if you want. Sure, sure, sure. Okay, more or less yes and no. So you're going on the right direction. So the technique to detect if there are fibers connecting different regions of the brain actually is based on DTI and is a diffusion things that they do. I'm not an expert in that, and is essentially taking an image of the brain and see that they can see how they are connected. But this gives me the physical connection between regions. Now, the other problem is I have a person, the person, let's suppose that I take an image through functioning magnetic resonance or whatever, or EEG, for instance, electroencephalogram, electroencephalography. And so the point is that for each region, we have the activation or no activation in the task. Great, then how can we know if two regions were connected? Well, there are different ways of doing this, and that's why I told you that this opens up the kind of a lot of possibilities. But the main idea is to see, okay, if I have two regions that activate more or less at the same time, it's possible that these regions are sharing some information between them. So imagine that you have two regions. Usually they activate and they activate completely like randomly. They are not connected, so they are each one of them is doing something about their own function. But suddenly I have a task, a given task, and then I see that they start activating and deactivated at the same time. Then probably the hypothesis that one can make is that both regions are contributing or are working together in this task. Therefore, they have to share information, and therefore that link is active. So these are called functional networks. Why they are called functional networks? Because the idea is that I don't know if there is a link between two nodes, but I suppose that the dynamics or the time series that I observe in each node is a function of its connections. So what I have to do is like an inverse problem in which I try to infer the connectivity given the dynamics. And the simple case is of course considering just a correlation. So I see that region A activates in a way that is perfectly correlated with what region B is doing. Then probably they are doing something together. They must share information somehow. And then I assume that that link is active. Are you following me, more or less? Okay, take into account that, of course, I'm explaining this to you and it seems easy, more or less, I hope, but reality is way more complicated because, first of all, there is the fact that two regions are activated at the same time. It may not mean that they are connected. Maybe there is a third region that is like forcing the activation of these two regions at the same time. And then I see like this correlation, but there is no causality between them. Uh, a simple correlation can give some information, but usually is not enough. So if you are in brain data analysis, you know that you have to see different frequency bands because each frequency band is supposed to transmit information in a different way. So this is way more complicated, of course, but as a first approximation or as a first idea, the point is, I don't want to see the physical network that is underneath the system that I am analyzing, in this case, the brain, just because the physical network is always there, is static, and does not depend on the task that I'm doing, and is not telling me what the brain is actually doing. It's more like what the brain could be doing at some point, but maybe now is not doing that. And functional networks is one step ahead and essentially says, okay, I'm now just looking at the data, at the dynamics of these different regions. And what I try to do is that I try to infer which one of those connections are actually active in this specific moment in time. It may change in the future. Maybe tomorrow you do the same task and the activation will be different. Or in a different task, of course, activations will be different and therefore connectivities will be different. But I try to infer the best as I can, because of course it won't be perfect, a picture of the connectivity associated to a specific task. And so, as you can imagine, this is way more powerful because then it's not just, okay, this is my brain and this is my network, and more or less it will be the same today and tomorrow. It becomes something dynamical in time, dynamical with the task that I'm doing, and therefore I can start comparing my brain at rest or my brain giving a talk or doing solving a mathematical problem. Try to see how the brain reacts to different things. And this is something that you cannot see in the connectome, in the just in the raw connections. So going back to the previous example, this is like to say, I don't want to see the roads, the structure created by roads in a city because this is too easy, it's static, it's always there. What I want to see is from where to where people move, and this will be different in the morning, in the afternoon, it will be different in a weekend, it will be different if I close one street because there are some work in progress, and then everything will change. So it's way more powerful, but of course, it's slightly more complicated because you don't have a network. You have to reconstruct your own network. And there you will have different ways of reconstructing it. You have different hypotheses and so forth. Depends on the data that you have. So it's really opening like a can with a Pandora box with a lot of things inside. It's very interesting, can be extremely useful, but also, I mean, some headache. You may have a headache doing that. So if this idea is more or less clear, what I want to do today is exactly reconstructing a functional network actually from brain data. So I've sent to you two files, time series subject 1, time series subject 2, and these are time series recorded with an EEG, so an electroencephalography of two people making a memory task. Uh, these data are free in the internet. I can send the link to you if you want. Essentially, if I'm not wrong, the task was a memory task in which the subject is presented with different images, and they have to push a button if the image was already shown before or not. So it's like a very simple memory test, just something fast. And the good point is that we have two subjects. One is a control subject. The first one is a, let's say, a healthy person, a normal person, and the second one is a person suffering from alcoholism. So the problem is, if you drink too much alcohol, even if you are sober when you do the test, I mean, you just drink a lot, like in the previous days and so forth. Would this change the way of the brain to communicate? Will the network be the same? The functional network in this task be the same, or it won't be the same? Because actually, when you make this test, you see that people that have problem with alcohol, they are slower at doing the task. They have several problems. So what you might expect is that there may be something there. That is that the two networks may not be the same. So without further ado, if you agree, let's start by loading the file so I can show you what is the structure. As usually, let's go with import numpy as np and also import network x as nx, because we will use them, let's say, shortly. And then let's load the network. The time series. So let's call this time series subject1 equal to np.load time series subject1 dot numpy time series subject2 equal np.load time series subject2 dot npi. Okay, let me save this as, I don't know, program, whatever, and then run it. Okay, now if I go to Variable Explorer, you can see that we have a structure, a bidimensional structure with 64 channels, and these are the 64 channels of the EEG. They're called channels. They are actually sensors. These are the sensors that are put on top of the head to measure the electric activity of the brain. And which one of them has 265 56, sorry, points in time. So it's 256 long time series, and you have 64 of them for each subject. Just out of curiosity, let's plot one. Yes, let's do the first channel for the first subject. Yeah, of course, because I'm missing this. And then if I plot, okay, here you have the brain activity of this subject during this task for the first channel, for channel number 0. That, if I'm not wrong, should be a frontal one, just if you are curious. So as you can see, okay, you have this nice time series. Now let's plot also for the second channel of the same subject. Let's plot this. So as you can see, they are not the same because they are two different channels, so two different parts of the brain, but you can see that they are actually quite similar. There should be quite a nice correlation coefficient between them. They're not strictly the same because here, as you can see, in the second channel, we go down to -20. I think this is millivolts. And here we just go down to -10. Then we go up to 20 here, and here we just stop at 15. So they are not exactly the same, which is good because it means that we are recording something that makes sense. But there seems to be some coordination between these two nodes, these two sensors, let's say. Okay, so you have the data loaded. Oh, okay, perfect. Then let's start creating the network. I will just use a very simple hypothesis, and is that two regions are connected, or they share data, or they collaborate in the task, or whatever you want to call it, if the, their correlation coefficient, the correlation coefficient between their time series is high, is important. So what I will do is that I will start by creating an array, an empty matrix of 64 by 64. Because now what I want to do is to calculate the correlation coefficient between all pairs of nodes, that is, all pairs of sensors. So for N1 in range 64, for N2 in range. And now what I will do is N1 plus 1, 64. Now you will understand why I say that this weighted matrix, that is the ways, like the ways, the how strong are the connections now between regions for subject 1 between nodes N1 and N2 is equal to, yes, yeah, sorry, I always forget. Yeah, I have a no, no, no. You're welcome, because I know that it's difficult to. I mean, when streaming, probably you don't see the screen well, and on top of that, I have this bad habit of having like a font super small while coding, and I don't know why. Probably because I like to see, a lot of the program just at a glance, but whatever. So I hope now you can see it better. So what I do is calculate the absolute value of np dot core coefficient, core coef, which is the correlation coefficient, between time series subject 1 of, this, time series subject 1 of N2, all the time series. So just to clarify what I'm doing here, I'm calculating the correlation coefficient between the time series for subject 1 of node 1 and node 2. Now, the correlation coefficient, if you know it in Python, the answer is all possible combinations. So if I do, like, for instance, this between channel 0 and 1, the output is a matrix in which the main diagonal is just, like, for instance, the first one is the first channel with itself, the other one is the second channel with itself that we don't need. So we just need to extract this 0.96. So here what I do is just at 0.1. And then, as you can see, I calculate the absolute value of the correlation coefficient. Why is that? Because the idea is that I'm looking at coactivation. So I want to see if the dynamics of two regions are more or less synchronized. But the point is that, okay, usually you may expect if region 1 is activated, then region 2 is activated. This will be a positive correlation, and then it's clear that I have a connection. But if I see that every time that region 1 is activated, region 2 is silent, and the other way around, so the correlation is negative, well, actually, this is not random, right? There might be something interesting going on. So what I do is that I calculate the absolute value, because a negative correlation for me is as good as a positive correlation, or at least this is a first approximation, but it tells me that there is something going on, even if it's negative. And then here what I do is that I calculate N1 for all 64 channels, but N2 just starting from the following. Why is that? Because the correlation coefficient between channel 1 and 2 is the same as the correlation coefficient between channels 2 and 1, so it doesn't make sense to calculate them over again. The only thing that I have to do here is say that Wm1 of N2 N1 is equal to Wm1 of N1 N2. So in this way, I'm sure that I will make a symmetric matrix, let's say. Then this is just for the first subject. As we are here, let's do also for the second subject. And what I will do, just copy paste. We just have to be careful to change 1 to 2 here so that we save in the correct, in a new matrix. And we take the time series for subject 2. But the procedure is exactly the same. Okay, let me run this. And then we have these two metrics. Let me plot it. So here you have this result in which, if I'm not wrong, let me see if I can. No, I cannot make this larger. Oh, well, I hope you can, or at least you can run the same and you should have the exact same results. Now, what you can see is that, okay, darker colors mean there is no connectivity or there is a lower, at least, correlation coefficient. And this yellowish green color means that, okay, there is a stronger connectivity between those nodes. So as you can see, this is not random. There are groups of nodes that are strongly connected between them. Like, for instance, from 0 to 12, more or less, these 12 nodes are strongly connected between them. Then there is another here from more or less 20 to 30. There is another here from 30 to 45, more or less, and then one last set. And as you can see, it's quite interesting because this group of nodes, that is the first community. At the end, these are like communities, as we have seen before. These are strongly connected between them, not so strongly connected with other nodes, but they are quite strongly connected with the third group. So it's like the first group is strongly connected with the third, and the second with the fourth. What is important here is, beyond this specific pattern of connectivity that then you have to study, you have to go back to understand which regions of the brain are these and so forth. But what is important is that clearly this is not random, right? So because if you have just random data and you calculate correlations, it will be just like a cloud of different colors. There will be absolutely no structure. But here you can perfectly see a structure, which tells us that something is going on. There are parts of the brain that are strongly connected together in this task, and maybe not in another task, but in this task, at least they are like very well connected. And actually what we can do, what we can do is plot the second subject. Okay, without doing too much mathematical things, we can see that it's different. It's not the same image. So I would say actually that the control subject has stronger colors. Like here in the middle, this second group of nodes from 20 to 30, you can see that in the control subject, they are like quite yellowish, so the connectivity is very strong. And then if we go here in the patient, we actually we don't even clearly see at least the communities, right? So this group of nodes is not that clear that they are very well connected between them and not connected with others. So it seems like that the connectivity in the brain is kind of more fuzzy for this person, something like that. But once again, what is interesting is that we have some kind of structure here, but this structure is not random, and we can see differences between the control subject and the patient. This is promising, let's say. Okay, of course, what we can do is something very simple. Let's calculate a matrix which is just the difference between both of them. So WM2 minus WM1. This is very simple. Run. So now this Okay, here you can see this is the difference between both of them. And as you can see, there is some structure. It's not that easy to see. Like we have a lot of green between regions. Uh, you can also just check out the data. Um, and here you can see, like, for instance, we have huge differences here. Then of course you have to go and see what this means, but it seems like that channel 1 and channel 16 are strongly connected. So this is positive. It means that the patient has a stronger connectivity than the control subject for this pair of nodes. But you can go here. This is amazing. So you have that channels or nodes 3 and 35, they are very strongly connected in control subject, but essentially no connectivity in the patient. So there is something going on here. Of course, then you should ideally go back and see which regions of the brain are and why you have this difference in connectivity. But as you can see, there are differences between the two people, which is okay. I mean, which is really good. Okay, so if you have reached this point, we can go on and create a more network representation, like the networks that we had in the last days. So for that, I have a problem. That here, as you can see, these matrices that I have extracted, they are a lot of numbers, but these are not links, right? Because usually what we want to see is which pairs of nodes are connected between them, or which node is connected to which other node. But here what we have is that each node is connected to all other nodes with different like degrees or different strength in the connection or different weight. So the easiest way to analyze this is just to delete those connections that we consider that are not really important or really significant. Or another way of seeing this is like, okay, we set a threshold. Everything that is below the threshold is noise. Because for instance, I don't know, zero point 0.1, this is probably noise. Yeah, you can get this value just with random data, so it's not important. What we want is this 0.95. So we set a threshold, we delete everything that is below the threshold, and we keep the network that we obtain. So this is actually quite easy. Let's say that threshold in this case is 0.9. So I want to delete everything that is below 0.9. Of course, this value can change depending on the applications or a lot of things. And then I will create the first adjacency matrix that will be equal to WM1 greater equal to threshold 1. So essentially what I'm saying is that I want to see only those elements of the variable WM1 which are larger or equal to the threshold. Sorry, threshold without the 1. And in order to make sure that NumPy doesn't do something weird, I will say that this is an array. This is the input, and the type equal to float. So I'm sure that the result are numbers and not booleans or things like that. I will also copy this for the second network, and I will run these two lines. Threshold is not defined, of course, because it was 2 lines above. Okay, now let's plot AM1 and AM2. AM1 and AM2. So remember, now what we have here is that the yellow dots represents links, where links have been defined as those pairs of nodes in which the correlation coefficient, actually the absolute value of the correlation coefficient, is larger than a threshold that we have set, that is 0.9. I mean, you can already see some quite clear differences. So first of all, in the upper part, you see that there are still these communities. like between nodes 20 and 30, and between, I don't know, 50 and 60. And for the patient, we don't see this structure. But what is most important is that for the control subject, we have many more links that for the patient. So somehow it means that the patient, the different parts of the brain of a person that drinks a lot of alcohol have a harder time to connect between them and share information. They are like, so imagine this is an orchestra and it's like that every instrument, every player is just playing something different and they don't connect between them. They don't synchronize in what they are playing. On the other hand, the control subject, the normal person, seems much more organized. There is like, a director that is like synchronizing things, and probably that's why the task is executed, let's say, in a better way. Actually, this is a result that has been demonstrated um, more or less in different, let's say, scenarios, not just with problems of alcohol, but conditions like Alzheimer's and in general several forms of dementia. What you have is that you lose connectivity in the functional network of the brain. It's like that the brain is not able so easily, at least, to share information between the different regions, and therefore any task will be like more difficult to execute, something like that. Of course, this you can take this with a pinch of salt, because of course it depends on the data that you have, how you do the experiment, and most important, how you define links. If you just do this correlation coefficient, well, you get these results. So now let's create, now that we have this, and if you open just M1, you can see that it's just a bunch of zeros and one meaning that there is a link, zero that there is no link according to our definition. Let's create the graphs and let's try to analyze them. So this is very simple. Now is what we did the last day. So I can say that G1 is equal to nx dot graph. So I initialize an empty graph, and then wait, I will do the same for the second. Sorry. Okay, I will do the same for the second network, just so we have everything together. And then what I will do is for n1 in range 64, for n2 in range n1 plus 1 64. Same trick, we don't need to repeat pairs that are symmetric. If am1 of n1, n2 is equal to 1, that is, if there is a 1 in the corresponding position of the matrix, then g1 dot add edge between node 1, node 2, and just in case, let's save the weight equal to wm1 of n1, n2. And of course, I can do the same for the second network, for the patient. Just be careful to change ones to twos. Okay, let's see what happens if I run this. So if I run this, I don't see anything. That's okay. I should have two networks. But now there is a small problem. Let's do g1 dot number of nodes. 63 nodes. That's weird. And if I do this for G2, for the second network, I have 41. Okay, why is that? Why I just have 41 nodes? I should have 64, right? The problem is that Network X creates nodes when we are giving to the library data about links that involves those nodes. So for instance, let's suppose that node 1 is not connected to any other node. The library will never see node 1 as such, and therefore will not create a node 1. So this tells you that in the first network, there are 63 nodes that are actually connected, but there is one that is not connected to anything else. And in the second case, you have 41 nodes that are connected, but there are other 23 that are disconnected from the network. And so this can be quite a problem because we know that we need the 64 nodes because this is what the network, how the network has been defined. So what I will do is something very simple here at the beginning. For n1 in range 64, I say that g1 dot add node of n1, and the same for the second network. So this is just to compensate for the fact that some nodes are not connected, but I still want a network of 64 nodes. So I don't want to just disregard a node because it's not there, because it's not connected, because actually it's there in the brain. We have that region. So it's not that we can just delete it and be happy with that. So now if I run this and check the number of nodes, we have 64. And in the second should be also, okay, I've done something wrong. Ah, yes, this is N1, not N2. My bad. Okay, so run again. And now we have 64. Okay, so now we have the network, the real network inside the library. Then now we can calculate some metrics as we did the other day. So what can we calculate that we may like? Let's go to assortativity. So let's calculate assortativity 1 equal to an x dot. Now the name was quite long. Degree Pearson correlation coefficient of G1, G1, and let's calculate also the assortativity of the second subject. If you remember, the assortativity is how likely are big nodes to connect to big nodes, or the opposite. Maybe big nodes are just connected with small nodes. So I will run this, and I have two quite different assortativities. So for the control subject, I have 0. Almost 6, and for the patient, I have 0.45. So there's quite a huge difference between the control subject and the patient. So it seems like that the patient is more random. So in the control subject, we have that big nodes are connected to big nodes and small nodes to small nodes. So there is like a rich club there of very highly connected nodes. And in the case of the patient, this value is lower, so it's more mixed. There is less structure, if you want. Okay, everything clear up to now? Okay, then let me make a quiz or a question to understand if you understood it well. So if we are looking at the propagation of information, because somehow this is like telling me how the information is distributed in the brain. So if it can move from one side of the brain to another in an efficient way and so forth. The most natural probably metric to calculate this, to assess this, will be the efficiency. If you remember, is how many jumps I need to go from one side of the brain to another one. Uh, can I calculate the efficiency in this case? Why I didn't do that? Just because I forgot it, or there is a reason why I didn't want to calculate the efficiency right now? Any idea? Okay, that's a good point, but this is the efficiency, not the average shortest path length. So if you remember, the efficiency is defined as the average of one over the distance. So it's perfectly defined even if there are no connections, even if there are isolated nodes. That's not a problem. So the efficiency will be like zero in a network that is completely disconnected and one in a network that is fully connected. Any other idea? Something that starts with Z and is a kind of score. I'm making this simple. No, okay. Um, there is one problem. If you remember, a sort of efficiency depends on the number of links that you have in each network. And the problem here is that we have two networks with two completely different number of links, because actually if I do g1 dot number of edges, the first network has 159 links and the second one has 80. So let's calculate the efficiency and let's see what happens. Uh, Efficiency 1 equal to nx dot global efficiency of G1, and efficiency 2 is the same but for network number 2. Okay, let's run this. And now what I have is that we have an efficiency for the first network of 0.17 and for the second network 0.8. So one may say, that's nice. So the control subject has a very high, much higher efficiency than the patient because connections are better or the connectivity is better. Well, actually, no. The problem is that we are comparing two networks that are not the same, that they don't have the same number of links. So, of course, I would expect a higher efficiency for the control subject, but just because it has the double of the number of nodes, of links, sorry. You have the double of links, and therefore you should be able to communicate better the information. But so the difference between the two of them is really significant, is really something, I don't know. What I have to do is go back to our friend that said score. So what we have to do is compare if this 0.17 is significantly larger or smaller with respect to what observed or what expected in random networks, and then we can get some conclusions. So let's try to do that. Uh, if you remember, the code that we used last time was something like that. So I create two empty arrays, random efficiency 2, then for let's do it, I don't know, 10 times. I have to create a random network, random graph equal to nx dot gnm random graph. So I'm creating a random graph with the same number of nodes as G1, number of nodes, and the same number of links, number of edges. Then I have this random network with the same number of nodes and links. Then what I can do is random efficiency 1 dot append, calculate its efficiency, and next dot global efficiency of random graph. Let's do the same for the second person. Would be G2, G2, efficiency 2. And finally, we have to calculate the z-score efficiency 1, which is equal to the real value that we observe, so efficiency 1, minus the average that we see in random networks, random efficiency 1, divided by the standard deviation of what we see in random network. Okay, and this also for the second. Efficiency 2, random efficiency 2, and random efficiency 2. So I will run this part of the code. And let's see what we have here. Okay, tell me if you should have similar results. Of course, these are random networks, so you may have values that are slightly above or below, but should be around these values, minus 44 and minus 16. Do you have them? Hello, did I lost the connection? You're still there? Okay, okay, perfect. Similar, okay. So yeah, as usual, if you get, I don't know, minus 40 or minus 50, it's okay, just the order of magnitude. But this is interesting. So yeah, tell me. Wow, it's quite a large difference, but yeah, let's do one thing. I will just run it with 100. So maybe, so of course the larger is the number of random network, the better, but of course it will take way more time. Okay, 1 second just to be sure. Okay. Still quite similar to what I got before. It's interesting. Are you sure that you have put well like G1 and G2, while copy pasting that you, because this is a mistake that I do like almost every time. You copy paste and then you forget to change what you have to do. Okay, in any case, it shouldn't be a big problem. I mean, maybe something, some small mistake somewhere else. In any case, so this is interesting because what we have is a set score that is negative in both cases. So this tells us that this network are not very efficient to send information to all the network. So this may seem weird, right? So a random network, it would be better actually to distribute the information. But if you think about that, it makes sense because this is not like a general task. This is a very specific memory task in which you don't want information to move around the brain like freely. You are not interested to distribute information throughout all the brain. You just want information where it has to be processed. So it makes sense because the efficiency at the end is a measure that tells you how efficient is the network to distribute information throughout all the network. But the brain is a very specific network or a very specific system, and in this task, even more. And so it's not just, I want to send information everywhere. No, no. I have a specific task in mind, I have an objective in mind. And so probably the brain is using a network for sending information that is focusing only on those regions that are really important for the task and not in general. And so here you can also see that for the control subject, it's more, let's say, inefficient than for patients. But we can see also the other way around. That is, for the patients, is more random. So you can also hypothesize that in control subjects, information is not distributed random. It's distributed specifically for the task that we want to solve. That is the memory task that we are doing. On the other hand, the patients are not as good to send information around in the sense that they're not focused. They send information everywhere or a little bit more everywhere than control subjects. So it's like, yeah, they are better at distributing information, but they are distributing information where information is not needed right now. They are more random. It's like, every part of the brain is working on its own. There is no coordination. There is no clear structure. So as you can see, I mean, the efficiency, you have to calculate it well with the Z score and all of that, but also can tells you things about the dynamics of the brain, and you have to interpret them according to the system that you are analyzing. That is, usually you think, well, a higher efficiency is better. Well, maybe not, because you don't just want to send information everywhere, you just want to send information where it's needed. So you don't want a very high global efficiency. You maybe want a very high efficiency in a specific subset of nodes. So you see the as I told you before, the complexity of this is not just one network. You can reconstruct networks of very different types, and then when you go and analyze them, you have to be careful because you have to interpret the results, uh, let's say, in the light of the system that you are studying. So maybe this conclusion that I just said is completely wrong for a network of proteins, because proteins maybe they interact in a completely different way, and that efficiency is always good. I don't know. So you have to be careful and adapt this to the problem at hand that you are studying. More or less clear? Any question or doubt or okay, let's just do, sorry, say again. Okay. Okay, perfect. Sorry, I just lost the connection exactly when you were talking. So, okay, let's go to to the last part. That is, okay, what we have done here, it's okay. This Z score is not very, I mean, it's okay, but calculating it is not very nice because we have to create a lot of random networks, and in many cases, it may be not such a good idea. And and also we have a problem that, as we have seen before, so if I go up here, uh, it's clear that there is a huge difference in terms of uh, connectivity or synchronization. That is, if I fix the threshold, if I say the threshold is 0.9, I see more connections in control subject and patients. But I might say, or I might wonder whether this is true if I just consider a network with n strongest links. So let's suppose that I want to see the network created by the, I don't know, 300 strongest links in both networks. So in that case, I don't care about the specific value of the connectivity of the correlation. I don't care if it's above or below zero point 0.9. But what I want to see is what is the structure created by the strongest links in the network, independently of the specific value. So you will see this quite easily, I hope, in the code. So what I will do now, I will define two thresholds. Threshold one, which is, I will write and then I'll comment what I'm doing. np sort, np travel 1. So what I'm doing here is, okay, first of all, I take WM1, so this matrix with all the correlation coefficients, and I ravel it. That is, I create one single array, one single vector, uh, unidimensional. So this is not important. This is just for making sure that Python doesn't do anything wrong. And then I sort the values that I have inside. So if I just run this, what I will obtain is a vector in which at the beginning I will have the smallest value, like 0, 0, 0, and so forth, and at the end, the largest value, 0 0.99, 0 0.999, 0 0.9997, and this is the strongest link that I have inside. Then what I do is that I select from the end side the element number 300. Let's do the same for the second threshold. So for the second network, let's run this. And now let's compare the values. So what it's telling me is that if I wanted to take the 300 top links, in the control subject, I need to set the threshold to 0.9, more or less as we had before. But if I want the 300 top links for the patient, I have to set the threshold a little bit lower to 0.86. But the important point is that if I now do the same that we did before, what I will have here are two networks with exactly the same number of nodes, 64, and the same number of links, because in both cases it will be 300, because I like adapt the threshold in order to be sure to have 300 links. So let's do this. I will copy like these two lines and these two lines, these two blocks. So here what I'm saying is that the adjacency matrix 1 is all the links which are equal or above threshold 1, and for the second subject is threshold 2. So let's just run this to see the effect, and I will plot AM1 and AM2. So what we have here is that the first network is more or less what we have seen before. The second network is different, but what is important is that it's the same number of links in both of them. And this, as you can imagine, simplifies all the analysis of the network, because then I don't have to care about z-score or whatever else, because I already know by definition both networks will have 300 links, so that's perfect. I can forget about everything else. Then I will make once again this creation of the network. It's exactly the same. We don't have to modify anything. So I can run this. Okay, I have the two networks now, G1 and G2. And let's calculate, I don't know, another metric like transitivity, for instance, the number of triangles. Now I can calculate the transitivity without doing any z-score, because it's already normalized. There are two networks with the same number of nodes and links, so I can compare. So transitivity 1 equal to nx dot transitivity of G1, transitivity 2 equal to nx dot transitivity of G2. Okay, I will run this. Now let's see the values. So interesting. In this case, there are not many differences. I mean, it's not a huge difference, but control subjects have a small, slightly smaller value of the transitivity than patients. Interpreting this, it's a little bit tricky, to be honest, and also because the difference is not that large. So I won't say a lot about that. I mean, but yeah, you may think that if you have a lot of triangles, I don't know, it's a little bit weird, right? You have region 1 that is working together with region 2 and also is working together with region 3. So it's a kind of redundant structure. Usually you want something more linear, like I want information to go from 1 to 2, then from 2 to 3. 3 will merge with 4, and then we will send information to 5. The fact that you have so many triangles could be problematic. Let's do one last thing, that is calculating also the betweenness centrality of nodes, just out of curiosity. So you can see what is the function. So BC1 equal to next dot betweenness. I hope I wrote it correctly. Centrality and BC2 for the second network. Let's calculate this. Okay, now the problem is that betweenness centrality is a measure of centrality of nodes. So as you can see, it's not that we have a one value for the network, but we have a one value for each node, which is quite inconvenient to represent in the screen. But let me see if I open the two vectors. Okay, and now we are carefully comparing them. So let's look for one vector for one node that is highly central in control subjects. We have, for instance, actually not a lot, 0.06. This is the largest that I've seen. 0.06 is 43. True, but I don't want to lose, okay, I don't like to lose the order, but yeah, 43 was the largest one. Yeah, then you can click again on key to, okay, yeah. In any case, look, 43, the most central link, node, sorry, in the network for the control subject, but absolutely not relevant in the patient, which is surprising. Then we have 7, that is the second most important. Let's see what we have here. This is actually important also for the patient. But also look at the values. So it seems that the centrality of nodes for the control subjects are more homogeneous than in patients. So patients has a lot of zeros, and here we don't have such an large number of zeros. I mean, I'm saying this just by looking. We can do better, of course. You can calculate. You can plot first of all the centrality of nodes, see if they are correlated, like in a scatter plot. You can calculate a standard deviation or whatever. So there are several ways. But what I would say is that what is important in one node, in one network, is not necessarily that important in the other. So like the third node here is 35, but 35, I don't see it here. 35 is, again, one that is not central at all. So it's weird. It's like, okay, you have two networks that are the same task. It's a brain, so you may expect the brain to be similar, but it's not. So if you look at the control subject, the nodes that are important are not the same as the nodes that are important for a person with alcoholic problems. And then, of course, once again, you have to go back and try to understand 35. What is a 35? So it's not just a number. It's a region of the brain that you have to check what it's doing, why it's important, or whatever. Uh, Also, one note of advice here is that we have just compared two networks. That is one control subject in one task and one patient in one task. Now, the problem is that each brain is different, and really is so. If you have worked with in neuroscience, that's actually a huge problem that we have. That is, there are so many differences between different people. So there could be more differences between two people, two control people, two standard people of the same age and nothing special, than with a person with a disease. In the sense that each brain is different, each one of us is different because at the end we are the result all of our genetics, of our evolution, or of our experiences in the past that is modifying the structure of the brain, the connectivity of the brain. So maybe we see this difference now, and then you check for a third subject and results are completely different. This may happen. So actually, if you do something like this seriously in neuroscience, what you have to do is that you have to take 1,000 control subjects, 1,000 patients, and then see if statistically these differences are, as statistically significant. But as a first approach, as you can see, is just calculating these metrics. And if you want to do it really well, I can also send you the files for a couple of thousand of patients. And then you calculate, you do the same process over and over again, maybe with a loop, not manually. And then it's a matter of comparing distributions and start checking if results are interesting. What I can tell you is that the reduction in connectivity in patients, specifically in patients with alcoholic problems, is a well-known fact. So it's known that alcohol somehow is disrupting the communication inside the brain, this capacity for creating functional links between regions of the brain. The reason of that, to be honest, I'm not an expert, so I won't speculate. But alcohol is not always good, let's say. So, what do you think? Any curiosity? Any other idea? Any question? Okay, I hope that this is well. We have seen this quite fast in the sense that these have been just three classes of 2 hours or 6 hours in total. Of course, it's not a lot, but I hope at least that you have seen that you have a global idea of what a network is, why networks are important, uh, especially that you can apply networks to almost any system out there or any data set that you have. By using these kind of techniques like functional reconstruction and so forth, you can create networks from, I would say, really any kind of data that you have, especially if they have a temporal evolution, like this one. You have different time series, you calculate correlations, and you can create networks. And then you can calculate metrics on top of that to try to understand what are the differences in the structure. Be careful with the Z score normalization and all of that. That is, you cannot compare networks with different number of nodes and links. But if you do this trick of the random networks, you are gold. You won't have any problem. And I don't know. I hope this will be useful for you in the future. I guess that for sure in this course on data analysis, you will find other cases where networks are used, especially with proteins and genes and things like that. But I especially hope that I don't know, maybe in the future you will find in your work or in your life in general some networks, and you will suddenly remember, ah, yeah, I remember 3 or 6 hours that we had with a weird guy that told us things about networks. So if you remember that, I would be really happy. Okay. Ah, yeah, please go ahead. Uh-huh. Hmm. Yeah. Yeah, and yeah, that's a good question. I've never seen that before, but it's not something completely new. I think that at some point I was discussing about this with someone, exactly doing this. So the idea was something on the line of, let's imagine that I modify one parameter and I see a change in the error or whatever target function that you have. Then I modify another parameter and I also see a variation. And then maybe I can calculate the correlation between these with the idea of detecting groups of parameters that have somehow, they're like communities that they have a common behavior. And then there are other parameters that are completely different and then they will not correlate with the remainder of the network. Things like that. Probably yes. I don't know how useful would it be, to be honest. I mean, this uh, it would be very nice to try actually. So if you do that, uh, you can send me an email afterward and tell me like, no, this was a very stupid idea, or yes, this was working really well. I don't know. It's in any case, it's a nice problem, so it's a nice possibility. If you have time and if you we all know how things are. So and also because if you have a lot of, yeah, please go ahead. Mm, indeed. Yeah, indeed, because if you find exactly parameters that are somehow connected between them, then it would be nice to see why. I mean, because maybe you have two parameters that, let's say, was name are completely different, but then that they are really connected in the evolution of the error. So I don't know. It could be okay. Yeah, just to represent them. Exactly. 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 Yeah. 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 That Sorry, say again. Ah, okay, sorry. Yeah, I don't know what happened, but I partly disconnected. Yeah, my headphones had some problem. Okay, so if you don't have anything else, uh, we can stop here. Have a good remainder of the course, and I hope you enjoy it. I'm glad. I'm glad of that. That's important. Perfect. Perfect. Really glad of that. Okay, very well. So that said, whatever any problem you have, just drop me a message and we'll keep in touch. Okay. Okay, thank you. Bye.